So, good evening, everybody. Hope all of you are doing well. And I also hope that you had the time to go through whatever we had discussed the other day, that is on Friday. So, just to give a 30-second recall on what we did on Friday, we tried to understand various kind of structure, several examples of structure property relationships. And in this, we started with the ferroelectric material, and then we came on to the radiation stability material. And I also tried to show you what is the key factor in the structure that is affecting, influencing a particular property. And why did we do this? The concept and the purpose behind that was to understand what structural factor is responsible for that particular property. And once we have an understanding of that, it would act as a very good key by which either we can tune or manipulate that particular structure to get a better property or improve property or change property. And also, once we know what are the structural factors behind any particular property that a material exhibits, that would also help us, that would also lay guidelines for designing newer, novel, better, improved material for that particular application. So that is the concept behind it. And in this context, we understood how the non-centrosymmetry in a structure leads to spontaneous polarization, and that leads to ferroelectricity. So we have a fair idea of that now. If we are looking for a ferroelectric material, the basic criteria is I should first go to the symmetry space groups which are non-centrosymmetric, right? And then in that particular space group, I can actually tune with the substitution in that particular structure, chemical substitution, or by other means to manipulate the transition temperature of ferroelectric paraelectric phase transition. Second example we studied was how pyrochlores, certain pyrochlores show high radiation stability or radiation tolerance. In this context, what we understood as a takeaway point was that if you have a borderline structure means structures who are present at the border of two crystalline phases, that is, who are amenable to show phase transition by only slight perturbations, would be the good material to design better radiation stable material, because the phase transition would act as one very good source to dissipate the energy deposited by the radiation in the material, thereby preventing its damage or crystal amorphization. All right. So today we will just look at some example of how the structure controls the ionic conductivity. Let's say ionic conductors. So all of us know what this is actually the Arrhenius formula for ionic conductivity or electronic conductivity or any other conductivity that we talk about, wherein let's say sigma is your conductivity, sigma naught all of us know we call as the pre-exponential factor. E is the activation energy for that particular process which we are looking at here, in this case the conductivity. Kb is the Boltzmann constant, which is a constant. T is the temperature that we are talking about. All right. Now, pre-exponential factor is not actually equal to, but can be correlated to the number of the charge carriers, the mobile species. Okay, and activation energy, all of us know, is the hindrance provided to the mobility of the particular charge carrier, be it electrons or be it ions. Okay, now if I look at this formula, so what can I say? That sigma or the conductivity can be increased either by increasing sigma naught, and what is that? By increasing the mobile species. I mean, that is a general sense that if you want to increase the conductivity, either you would want to increase the number of charge carriers, or you would want to make the conditions suitable for them so that they're mobile enough. they can easily carry without any hindrance. So here in technical terms, we represent it as sigma naught, the exponential factor. You would want to increase it, and or you can increase this value by decreasing this exponential, the energy term that is a negative exponential. That is by decreasing E or by decreasing the activation energy for that particular process we are talking about. In this case, movement of ions, or you can manipulate both, but in the favored directions. Okay. So, by increasing pre-exponential factor, we mean that we need to increase the mobile species. And when we talk of decreasing E or the activation energy, that means we are providing unhindered pathway to our charge carriers for migration. Now, if I go to the pyrochlore and fluoride structure, not exactly fluoride here, defect fluoride. Now, defect fluoride, all of you know, I described in the last classes. In the fluoride structure, if you remove some of the oxygen ions, create some vacancies, and they are randomly distributed over all the unit cells, we get a defect fluoride structure. Okay. And in that particular thing only, suppose your vacancies or the oxide ions are ordered, and A and B cation are also ordered. You get a pyrochlore structure. Okay. Now, if you have a fluoride structure, if you have a disorder in the structure, now it is very easy to imagine that there are a lot of mobile charge carriers because there's a disorder in the material, right? So you have more charge carriers available. But in the pyrochlore structure, because your vacancy and the oxide ions are kind of fixed, so number of mobile charge carriers are not much. But because there is an order, so there are proper pathways for your oxygen anion, which is a charge carrier in this particular case, to move. Okay. In very, very simple way, in very, very crude way, if I try to explain it to you, suppose you have wooden sticks, okay, and they are arranged like this. Assume this is a pyrochlore structure, and in case of disordered fluoride, the sticks are arranged like this. Okay. Now here, because in this particular situation, since there is a disorder, so almost all of them can move. So the number of charge carriers are more. But once they move, they will provide hindrance to each other's movement. There will not be any smooth mobility. But in case of pyrochlore, even though they are kind of fixed to their positions, but they have very clear pathways wherein they can move. That is, the mobility is higher. That means if you have an ordered pyrochlore structure, you have lower E because the activation barrier is lower. But then in that case, your pre-exponential factor is also low, number of mobile charge carriers. In case of disordered fluoride, you have higher mobile charge carriers, higher concentration of mobile charge carriers, but the activation energy is also high because they're kind of hindering each other's movement. What we desire is we want lower E and we want higher sigma. This can be obtained by optimization of the structure, which can be done in many ways, and one of the ways is by controlling the substitution. Because if you remember, I told you in the last class that by varying RA by RB, rather by controlling this particular factor, I can very slowly move from a defect fluoride to the pyrochlore. I'm moving from disorder to order region. And this is one key by which we can control the degree of order or the degree of disorder in the material that will ultimately manifest its effect on the ionic conductivity. Let us see. So what is the strategy? You basically take a pyrochlore material and try to introduce disorder in it. And how can we do it? As I discussed, by tuning the ratio of the radii of cation A and B by introducing some other ion or a hetero ion. Okay. Now let's say in this particular slide, in this particular work, this was done in R group. We took GD2ZR207 which is exactly at the borderline. It is a pyrochlore, but it is highly disordered pyrochlore because it lies at the borderline of the defect fluorite and the pyrochlore structure. Nd2Zr2O7 is a fairly ordered pyrochlore. So what we did is, what was done in this particular work is, we took Gd2Zr2O7 here, which is denoted by zero amount of Nd, and we started putting Nd in it. That is, we are going from gadolinium zirconate, substituting 10 by or 10 of gadolinium by 10 of Nd, 20 of gadolinium by 20 of Nd, and so on and so forth till we reach pure Nd2Zr2O7. So what we observed in this particular, of course, these many compositions were synthesized and they were characterized to make sure that all of them are pyrochlore. Okay. So then we did the conductivity studies wherein we obtained the activation energy and the pre-exponential factor. So what was observed was that the activation energy, as we go from gadolinium zirconate to Nd zirconate, that is from less ordered pyrochlore to the more ordered pyrochlore, the activation energy is decreasing. That is, it is now easier for the charge carriers to move. They're facing less hindrance. But on the same side, concomitant with increase in Nd, your pre-exponential factor is also decreasing. If I combine these two by this formula, the Arrhenius formula, and we determined the conductivity, what we observed was that as an effect of these two, at the concentration where both Nd and Gd are equivalent, that is 1 is to 1, that is the composition now NdGd Zr2O7. We got conductivity maxima by the compromise of decrease in activation energy and increase in pre-exponential factor. So what basically this is doing is, decrease in activation energy is improving the ionic conductivity, but the decrease in mobile number of species is reducing the conductivity. So somewhere in between they reach an optimization and conductivity is maximum for y is equal to 1, that is for this particular composition. Okay. So what we did here is we tuned the structure. We controlled the structure by controlling the composition. And what is composition doing? Nothing. But you are actually playing with the radius of the A cation so that you can tune the ratio of the radii of A and B cation. Okay. So another example, will not go into it. Now, going to another applications, okay. You would have heard about ion exchanges. Now these are the classes of material which have various applications. They are used as sorbents for purifying water. They are used in our nuclear industry for taking up harmful fission products, which are strontium, cesium, and then these materials take up the harmful product, and similarly for the purification of water or sorption of like toxic elements like lead and all, they take up this and they give out a rather harmless cation. Okay, so that harmless cation is a part of the structure of ion exchangers. They are put into the stream, whichever we want to clarify. They take up the harmful cation and give away the harmless cation. And energy storage. So I think half the material scientists are working on the field of energy storage. That could be in the form of batteries, supercapacitors, dielectric capacitors, and so forth and so on. Okay. Now these are only few of many classes which use layered materials. What are layered materials? Okay, not something you read of the layered structure in your second class as well. The structure of CDI2, wherein the bonding is such that two layers are strongly bonded to each other, but they are only weakly bonded to the third layer. And this gives the material a layered material kind of property. So layered materials are those material wherein the crystal structure is such that it has got two-dimensional layers which can actually hold many intercalated cations or water molecules or other species, which are actually very important for their properties such as ion exchanging and energy storage. Now, suppose I want to, I just told you a few minutes back, in the nuclear waste stream that we obtain, there are two harmful fission products, strontium 90, let's say strontium 90 and cesium 127. Now I want to remove strontium 90, okay? If I have a layered material which has got sodium ion, now sodium ion are harmless, sodium ion in its between the layers, and suppose the structure is such that it is ready to let sodium ion go away, and it has the affinity for strontium ion such that it does not release strontium ion once it has taken up, then that can be used as ion exchanger for taking up strontium from the waste stream. Okay, so this is one such material which is called sodium or potassium birnacite. It is nothing but a type of MnO2, one of the polymorph of manganese dioxide. What is the structure? It has got layers of MnO6 octahedra, and in between these layers, we have got sodium ion or potassium ion or both, along with water molecules for the stabilization of the structure. So this is how your structure looks like. Okay. So what does this do? Now ions which are present in between the layers, what happens is these layers, why do these layered material have got ions in between the layers? In your cadmium iodide structure that I taught you, there was no interlayer anion, interlayer cation. This is because these layers have got a residual negative charge. To balance this negative charge, the monovalent sodium or potassium ion, they are accommodated in between the layers. Okay. So, of course, the ions which are present between the layers to compensate the residual charge of the layers are the ones that can be exchanged. So, mind you, these manganese ions in the layers will not be exchanged. They're tightly bound. It is only these labile ions which are in between the layers can be exchanged. Okay. So, this is one example, as I told you. Then K2ZrPO4 whole twice is another series of compounds. Okay, so these are the materials which we can use for. So what we do is we take this material, it is in the form of powder, we put it in the nuclear waste stream, the sodium goes out, the strontium comes in, and once timely they would test it, they would test the stream for the presence of sodium to strontium ratio, and when they're satisfied that a lot of strontium has been taken up, then these materials would be taken out. Okay. So, yeah. Similarly, cathodes for lithium ion battery. Okay. Your present day lithium ion, your present day smartphones, the batteries has got electrode as lithium cobalt oxide. Okay. It has its own disadvantage. So people are working on various other electrode material which can give you better charge life. Once you have charged, you would not want to charge your phone again and again. That is the reason researchers are working on better materials to act as electrode for your lithium ion battery. And one of this is NMC electrode. Why NMC electrode? Because instead of cobalt, it has got nickel, manganese, and cobalt, all three of them. Also, another material that is being researched is LiFePO4. Now, what is the speciality of all these materials? Lithium cobaltate, or lithium NMC, or lithium iron phosphate, is that they are all made up of very rigid tetrahedra. Okay, in this case, let's say PO4 and FeO6, polyhedra, tetrahedra and octahedra, and the lithium ions are present either in between the channels or in between the layers. And these lithium ions, let's say, when I am charging your material, they will move out of this electrode, go into the electrolyte, and go to your anode, which is cathode, which is carbon. Okay. Now it is charged. Once you discharge it, this lithium ion will come back from your carbon to electrolyte to this particular lithium anode, which is present day Li lithium cobaltate, but they are futuristic material like LiFePO4 and NMC electrodes. Now, what is the conditions that this particular material can act as electrode? A, once you are charging, it should let lithium go. B, once the lithium has gone out, it should not crumble. C, it should be able to take back the lithium in. And all these things should happen without causing any damage to your crystal structure. Okay. So how is it? Of course, there are many other factors. Not all the material which have got intercalated lithium will let lithium go. Some of them will bind it hardly, strongly. Okay. So how in this particular case, what happens is, this is your LiFePO4. Some of the lithium will go and it will form Li1 minus X FePO4. Now, how is the charge neutrality maintained? Because Li was there in between the columns, in between the channels. Once Li plus is gone, the positive charge of the material has come down. If it is not electrically neutral, the structure will crumble. So what happens is concomitantly, this Fe2 plus goes to Fe3 plus. Okay, that means once Li plus goes away, one positive has gone, Fe2 plus gives away the electron to get Fe3 plus, and it is this migration of electron that flows in the outer circuit as current. Okay. Similarly, we can have sodium ion batteries within this FePO4, though any is not as good an electrode as LiFePO4, but this has also been researched a lot. So what basically we understood today is we need to know the application, what I'm looking at. We need to know the structure, how the structure gives rise to the property, and if I know the property, for example, my ion exchanger, my batteries, my supercapacitor, they need to have the structure from which the ion should be able to readily move in and out without any damage to the structure if I want long cycle life. Then I know I have to look at the material which have got layers. I also have to look at the material which should have a cation which can undergo difference in oxidation state once my lithium or sodium ion goes out. Okay, so you know what should be the structure, you know what should be the factors that should be present along with this structure. This would give you a fairly good idea of how to design your material for a particular property. Okay, so what basically we learned in last half an hour in this class and half an hour of the last class is functionality is strongly dependent on its crystal structure. As we will read in the next lecture, it is not just only the crystal structure, but still crystal structure is most important factor that contributes to the functionality of the material. If you are planning to design the material, you also have to understand design of the material for a particular function should consider the functional requirement. Basically, what is it that I'm looking at? If I want to have an optical material, luminescent material, what is it that I'm looking at? I need to look at the band gap. Okay, that means I need to look how my atoms are placed in the crystal structure so that they would give an appropriate band gap. Okay, suppose I want to design an ionic conductor. I need to look at the structure which will have mobile species. If there are no vacancy, no defect, no mobile species, your material can't conduct. Okay. Ionic conductor I'm talking about. And just having the mobile species is not sufficient. You have to give the ions also the pathways to move. So the structure should be such that it should have proper pathways. Also, suppose your cation, suppose it is a cationic conductor, let's say lithium ion conductor. In that case, your anionic lattice should not be very hard and rigid, because if it is hard and rigid, it will not let your cation move. And that is the reason you can mark that in your book also. Sulfide ions are better conductor than oxide. Sulfide containing materials are better ionic conductor than oxides, because sulfur is a bigger ion. It does not hold your cation as strongly as your oxide ion. So these little understanding of the thing will help you understand what you want from your material, and that will help you design your material in a better way. Ion exchange requires either tunnels or layers, some space where your ion can move. Radiation stability, phase transition borderline structure was one such criteria by which you could ensure the mitigation of deposited energy. Howsoever, you need some mechanism. If it's not phase transition, it could be anything else, wherein that excess deposited energy can be mitigated. So, what we want to say is that if you have an idea of what you need and what are the structural parameters that favor that requirement, even the tweaking of the existing material is very much possible to obtain superior properties. Okay. So, with this, we take 2-3 minutes break before moving on to the next topic. Your doubts are most welcome in the chat box. And I just typed in, but just to remind you again, lecture we are not conducting the lecture on 21st Wednesday. And now the next lecture after today shall be only on 23rd, which is Friday. Okay. Is there anything from the last three or a little more of the lectures that you would want to repeat? Okay, we can move on to our next topic. Okay, so this particular topic is about defects. Why do we study about defects at all? You know, something where the name is defects. What is there to study about it? But to be honest, most of the properties in the materials that we observe around us, they originate only from defects. Okay. So, what are basically defects? Defects are imperfection, very, very simply defined. There are various classification of defects that we will talk about in, say, next 50-55 minutes or so. Very simple layman definition of defects is if in a regular geometric arrangement, you've got imperfections. That is what we call as defects because they're not following the regular order that has been repeated three-dimensionally. Do they affect? Of course, they affect the properties that you name, mechanical properties, optical behavior, chemical reactivity, electrical properties. Almost all these properties are affected by the defects. Of course, different kind of defects, which we will talk about in, as I say, next few minutes. So, you know, perfection, it's always said that perfection is boring. So, actually, solids are also like people. They're like you and they're like me. None of us is perfect. We have our imperfections, we have our defect, but that only make each one of you us unique. That only make us unique and interesting, if at all, in our own ways. So, similarly with the material, it is actually the defects that makes them interesting and impart most of the important properties exhibited by them. Okay. Uh, as I told you just few minutes back, I told you that crystal structure is one of the most important factor that contributes to the properties. And by controlling the crystal structure, it tune or modulate the properties. Okay. So basically, if you ask me, what are the three things that contribute to the property? That would be bonding, chemical bonding. But ultimately, if you see chemical bonding, the nature of the bonding is or will also affect the crystal structure. So they are anyway interrelated. But still, for the sake of naming, I would say the properties of the material, the macroscopic property. When we say macroscopic property, the property that you can see that they exhibit depends upon the bonding, its structure, and other than these two, the defects present in that particular material. Okay. Honestly, sometimes you need the defect to show the property. Okay. Material like zinc oxide, the only luminescence that it gives, it depends upon the oxygen ion defect that exists in zinc oxide. Otherwise, its band gap does not fall in the visible light. So what I want to say here is defects are nothing but necessary evil. For some particular properties, you need to have those defects so that you can get the property. For example, if you have a perfectly crystalline three-dimensional arrangement of ions, okay, you cannot make an ionic conductor out of it. Why? Because the ionic conduction requires the pathways. In some class or the other, you would have heard about hopping mechanism. Okay, let's say you imagine like the students stand in the prayer ground. They make rows. Okay, if I want a student standing in a corner of first row to come to the corner of third row, it is very difficult if I don't allow him to move between the rows. Okay, but if I, let's say, remove a student standing in the adjacent row to the row from where I want the student to come in, he can hop into that vacant spot. Okay, then somebody can go into that vacant spot and another vacancy would be created. That vacancy would be filled by another neighboring student and so on. So what I mean to say is this is similar to what I was trying to explain is ionic conduction. if I want the conduction to happen, I need to have empty spaces. And more often than not, those empty spaces are contributed by vacancies or the defects. Okay. So how and why do they occur at all? First of all is thermodynamic reasons. Many of you would have studied about all this, but there's no harm in revising it, so let's just go through it. For thermodynamic reasons, means your material will not be stable thermodynamically unless and until you have those defects. So thermodynamic defects are those defects wherein you go into the bestest lab in the world, you work in the most sterile conditions, those defects will creep in whatever you do. Those defects are called thermodynamic defects, okay, which are required, which are essential for the stability of the material. Or by deformation of the crystal, once the crystal is formed and then it is deformed, that will create defect. Suppose you are making single crystal or you're working with the polycrystalline solids also. You've heated it to the higher temperature, let's say 1400, 1500. And what you do is from 1400, you don't let it cool. Rather, you quench it. Quenching, what is meant by quenching is rapid cooling. That is, I take my container that contains that solid immediately out from 1400 to room temperature. Or worse still, from 1400 to I drop it in liquid nitrogen. That is called quenching or rapid cooling. Now, whatever at high temperature, you can very well imagine that material would have been highly disordered, they would have been in motion. Now, if I slowly cool it, I give it the time to go back to equilibrium. But if I suddenly bring it to the room temperature or liquid nitrogen temperature, it sometimes it happens, it doesn't get time to settle down, and that it would whatever, let's say they were vibrating very fiercely, then sometimes what will happen is that if you quench them, they would be forced to be in that particular position, creating the defects. Exposure to perturbations like high temperature, high pressure, or radiation also leads to defect. Or during the synthesis process, you have provided it some disturbance or perturbation that can also lead to defect. So basically, if you have imagined, all of these are extrinsic condition, while this is the intrinsic condition that cannot be prevented. Okay. So when we talk of defect, we'll talk of many defects, okay? But what are the very basic defects? That are vacancies, that is the atom has been removed, which is shown here, or interstitial, that is some atom which was not required, it has come there and occupied the interstices between these spheres. Those are called interstitial. So by strict definition, vacancies are unoccupied atom sites, whereas interstitials are an atom occupying an interstitial site. Okay. So how can I classify the defects? There are many types of defects. How can I classify? Now, why do I need to classify it? I mean, as a student, I should ask, why do I need to classify it at all? So we need to classify it because, when people who work in defects, of course, we will not be talking about those advanced defects here, but sometimes it is easier to observe a new thing, and by virtue of, let's say, I've been able to observe two or three properties of a particular thing, and that belong to a particular class, then it becomes easier. And if I'm able to classify to the particular class, then there's a high probability that I've been able to observe only two, three characteristics, but the other 10 characteristics associated with that class would also be belonging to, would also occur in this also. Okay. So that is the reason we classify the things, not just in case of defects, but wherever we classify, that is a very important reason for classifying, so that some things you discover, some things you are able to allot to it. Okay. So the classification of the defects is based upon many factors, thermodynamic factors, dimensionality, we'll study about it, whether the defects are intrinsic or extrinsic, and the stoichiometric changes. Okay. Whether the defect that has occurred has brought any stoichiometric change also in your compound, or it has left it undisturbed. So let's talk about thermodynamically generated defect first. Give me a second. All right. Okay. So why, what is the main reason behind the thermodynamic generated defect is the defects introduce disorder that increases entropy and that decreases the free energy. This lowers the free energy of the system, and this is the reason that some amount of defects, it is necessary for the material, some amount of defects generated helps in lowering of the energy of the material, and hence they are invariably created in the material. So there are two types of thermodynamically generated defect. Schottky defect, which all of us know, is a pair of missing cation and anion vacancy. And Frenkel defect is a pair of vacancy and interstitial, nothing but an atom has been displaced from its side, crystal side, to uh, the vacancy, and that uh, forms an interstitial, and the couple of this interstitial and vacancy that has been formed by this atom displacing is called the Frenkel defect. Okay. So, Schottky defect, this is your regular crystal structure, absolutely three-dimensional periodicity, 3D arrangement, no problem. You remove a green ball, which is a chloride ion, and a red ball, sodium ion, and this pair is called the Schottky defect. So Schottky defect is not one chloride defect or one sodium defect. It is a pair of a positive and negative ion missing from their usual lattice side. Okay, because simultaneously you are removing equal number of sodium and chloride ion. So this particular defect makes does not disturb electroneutrality because both the charges are getting removed at once, and also the overall stoichiometry is also not disturbed. What do we mean to say by here? This was NaCl and this is Na.99 Cl.99, which can also again be written as Na12Cl. So it does not disturb the electroneutrality, it does not disturb the stoichiometry. Okay. Frenkel defect, perfect lattice AgCl. This particular Ag decides that it doesn't want to stay here and it goes into the interstices. Now this couple, the vacancy and the interstitial, together constitute Frenkel defect. Now here also, nothing is going out of the lattice, nothing is coming into the lattice. So the overall stoichiometry is unaffected. You have equal number of vacancies and interstices. Just another cartoon to replace these two particular defects. This is your uh, Schottky defect, and this is your Frenkel defect where the atom has gone into the interstices. Okay. Now, let's say on a particular lattice, in a particular material, let's say NaCl, the Frenkel defect means moving of only one type of atom into the interstices. So whether it would be anionic sites, anionic lattice that would support the Frenkel defect, or whether it is a cationic lattice that would support the Frenkel defect. So it can occur actually on any of them. But in a particular material, it is only one lattice site that supports it in general. Okay. Now, cation Frenkel defects are more common, very simple, because cations are generally smaller and interstices are smaller than the material, than the ions forming the closed packing. That is why it is easier for the cation to go into the interstices. However, in case of calcium fluoride structure, we talk of calcium forming FCC lattice and fluoride occupying the tetrahedral hole, because in this case your anion is smaller. For the same reason, the material like CaF2, SrF2, zirconium oxide, uranium oxide, they are better at accommodating anion Frenkel defects and not the cation Frenkel defects. Okay. Just a small explanation of whatever we just talked about the thermodynamic. Okay, Schottky and Frenkel are your thermodynamic defect. Just to repeat that. And this is only a small schematic which shows why these effects are thermodynamically favorable. Okay. Now you consider you have a perfectly ordered three-dimensional periodic lattice. Okay. You remove one atom. Now, of course, once you are removing one atom, you have to break all the bonds because it is surrounded by neighboring atom 4, 6, 12, whatever is the coordination number. When you want to break the bond, energy is required. So this is endothermic. Okay. Now let us remember that delta G is equal to delta H minus T delta S. Right. So this is positive. But suppose it was completely ordered and you want to remove only one atom, right? Now you have a lot of choice which atom you can remove. You can remove it from here, you can remove it from that position, from this position. So this freedom that you have to remove any atom, that is actually called the configurational entropy. That is number of states it can adopt. Okay. Now, so what basically right now I would talk about is creation of defect will need energy. So delta H is positive, but creation of defect will increase disorder. Forget about the configurational entropy right now. You are creating a defect, you're creating a disorder, right? So delta S is positive. Okay, H is positive, S is positive. Now, if this term temperature is positive, of course, if this term is positive and this is also positive, then the free energy would increase, and this is increasingly positive. So this term is increasingly negative. So the free energy delta G would be negative. If it is negative, means it is a spontaneous reaction. Now let's say you have to remove 10 atoms. Okay, 10 atoms, again you will have to break bonds associated with the 10 atom. So delta H, the enthalpy change will always be positive because you are breaking the atoms howsoever number of atoms you remove. But suppose you have already removed, the material was perfectly ordered and you removed one. The change in entropy was too much. Now the material is, you just imagine ocean. The waves are there, okay? If you just put a stone in it, it will create disturbance. But is that delta S, that delta disturbance, anything in front of already that disturbance is present on the ocean surface? No. So when your material already has a lot of number of defects, delta H is still positive, but delta S is now not that much positive. That is, you are somewhere here. Now, S is kind of, the slope of S is kind of, not decreasing that much, but this is still positive. So your delta G will become positive. That means now your reaction is not, whatever process you were talking about, in this case, creation of defect, is not thermodynamically stable. So somewhere in between, delta H would be equal to T delta S. And this is the point, if I'm plotting it energy versus the defect concentration, the number of defects that I'm creating, somewhere here your delta G would be minimum, would be zero. And corresponding to this particular n is the amount of the defect that would be present in your material, howsoever hard you try, by virtue of entropy driven stabilization. I hope I'm clear. Okay. Another thing that you should note about is that if I increase the temperature, let's say whatever story I was telling you was at room temperature. Now I make it 300. Now, when you make it 300, everything else remaining thing, now this term is bigger. Okay. This term will be able to fight with this term till larger number of defects. And this G would be somewhere like this. Okay. Now, the number of defects that your material can accommodate is more. That means equilibrium defect concentration increases if you increase with temperature. So the 2 points that we take from this slide is thermodynamic defects are necessary for entropy imparted stabilization, and increase in temperature will lead to increase in the number of thermodynamically created defects. Just one point I would want to repeat. I talked about configurational entropy. Configurational entropy is basically the freedom given to the material, the number of ways by which that material can adopt a particular state. This particular entropy is called configurational entropy S, and it is given by K, Boltzmann constant, log natural WB. WB is the probability of attaining that particular state. Okay. Now, which defect would be created? Let's say I'm not talking of ionic crystal. I'm talking of metal. Metal can have only defects of vacancy and interstitial. It cannot have Schottky defect, right? So, which defect is easiest to form? The defect which has smallest delta I. Like you and me, the material would also prefer the thing wherein it has to work less. It has to give take lesser trouble. It is lesser endothermic. Also, for which the free energy minimum occurs at highest defect concentration. That is, which imparts higher entropy. All right. So that is the reason your rock salt kind of structure shows Schottky defect, but not AgCl and AgBr. They are also low rock salt, but they show Frankel defect. So both the things come into being. The need for delta H to be positive, the need for delta S to be positive again, more positive. Okay. Now, this is one particular derivation where I will only tell you the logic behind it. We need not do the derivation. You can simply go through it. Most of you would have done it also at some stage in your solid state course. Okay. So this is only how can I correlate the number of defect produced thermodynamically with the temperature T. Okay. Simple. We talk of configurational entropy, that is K, S is K log natural W. W, I told you, is the number of ways by which, suppose I want to create this small ns defect and my total number of lattice sites are bada N, capital N. I want to create this defect on these many sites. So the number of ways by which I can distribute these ns over all the possible n sites is called W. And if you go back to your probability that you studied in 12th standard, that is given by n factorial upon n minus n factorial, small n factorial. Okay. Or it is a number of ways suppose I'm talking of Schottky defect. Schottky defect means one Schottky defect is equal to one cation vacancy plus one anion vacancy. So number of ways I can distribute cation vacancies is this. Number of ways I can distribute anion vacancies is this. Now, if I want to calculate total probability, now you remember in your probability, if you are talking of two things, you multiply them. So the total probability is WCW. All right. Now, because these two are equal, because I will create equal number of cation and anion vacancies. So this will be W square. Okay. Now, if I replace this in K log natural W, I will get something like this. This is square. Now, since this is log natural, I can take this 2 here. It is 2K log natural, this particular factor. Now, n we know is Avogadro's number or even more than that, right? For the values of n which are much, much greater than 1, this can be simplified using Stirling approximation, which says that log natural n factorial, because when you open this bracket, it will come out to be 2k log natural n factorial minus 2k log natural n minus ns factorial and so on. You have to apply the formula this. So once you do this, you open this up and you'll get something like this. Okay. Then your delta G is NH minus T delta S. This was only delta S multiplied by T. Okay. And then put this N delta S. And then because remember this figure, I want to calculate defect at the minima with respect to defect concentration. That means I differentiate my free energy with respect to number of defects and equate it to 0. You will get something like this. Now, okay, this is only the differentiation shown, and then you will arrive at this. It is a very simple differentiation. That is why I don't want you to do it. Only understand it. Going through the derivation, even if you cannot do it, it clarifies your concepts because of so many approximation. Why are you putting that approximation? That helps you understand. Now, similar, like you have now arrived at this, okay? But now we know that the number of lattice site that is available to me is much, much more than NS, right? So I can make this as 0, and then this will reduce to this particular thing. Or because this is a Boltzmann constant, if I want to talk of moles, I replace K by R, and that is it. So you here what you have equated, you have equated your equilibrium number of defects, Schottky defects created at a particular temperature T. And why do you have 2 here? Remember, because here you did square. Why you did square? Because you wanted to talk of the Schottky defect, and there your cation vacancies are equal to anion vacancies, and total probability would be the multiplication of this. But now, another small tip which you should always remember, if I'm talking of only vacancy or only interstitial, they do not occur. I mean, of course, the Frankel defect is a pair. It is a pair of vacancy and interstitial. But ultimately, and in case of Frankel defect also, this formula will hold, right? But in case of metals, where you have additional interstitial, because there, the concept of electron neutrality does not hold. There, this W will only be just one factor. And when it is one factor, you will not have a square here, and hence you will not have a 2 here. So for a simple vacancy and interstitial, your formula would be Ns is equal to N exponential minus delta H S upon RT. But for Schottky and Frankel, you will have this 2 in the denominator. So most of the time, these are certain things that you need to remember for any numerical, for any understanding that you can come across. Okay. Now, just, we just talked about why, we can talk about why some materials show only Schottky defect and some show only Frankel defect. Now, here I would want to clarify one thing. Okay. I would tell you, and the textbooks would tell you, that NaCl shows Schottky defect and silver chloride shows Frankel defect. But that doesn't mean that NaCl will not show any Frankel defect at all, and vice versa for silver chloride. Okay, it is only that energetically a particular defect, Schottky in case of NaCl, is more favorable, and that is the reason it will happen in the content of this will be much more than the other, so that effectively it is in a very small amount, so we don't count it. But all the defects are created in a material, whatever is possible. Okay, now there are many reasons why NaCl shows Schottky and AgCl shows Frankel, but we can definitely talk about one simple reason in a schematic that would help you understand. Before that, remember both NaCl and AgCl have got rock salt structure, same structure but different defects. Okay. Now this is the section of your rock salt unit cell. Why do I say section of the rock salt unit cell? Because this is not the complete unit cell. Now what is your rock salt structure? I would have loved it if you remember it now, by now. But if you don't, I will repeat it for you. Imagine your Ag is at the corners and the face centers. In that case, your chloride will be at the edge centers and the body center. Now you just imagine 1/8 of that cube. Okay. This Ag is your cube, corner of the cube. These two Cls are the ones at the edge center. This Ag is the one at the face center. And this is at the edge center. this is at the body center, this is at the face center, and this also is at the face center. Now suppose your AG wants to go to, it's making a Frankel defect. Now this is the interstices that is present. It will go into this particular interstices. Okay. Now imagine instead of AG, if you had NaCl. Now Ag is a bigger ion. It is not that polarizing, but Na is a very hard ion. Hard means it has lot of large charge by radius ratio. Now for such an Na plus here to have been surrounded by four equally hard Na plus on the corner, it would make it energetically very unfavorable and it will not prefer Frankel defect. That is the reason it adopts Schottky defect. Whereas in case of silver, it is kind of a less polarizing cation and it also stabilizes by forming some covalent interaction with both silver and chloride surrounding it in this particular interstices. Okay. So the more electropositive, harder Na plus not preferring to occupy an interstices which is surrounded by four equally hard sodium ion compels it to go for Schottky defect, which is more energetically favorable for this. Okay. So yeah, this is nothing but it shows that as you increase the temperature, there's a tremendous increase in the defect concentrations. Okay, we'll take a 2 minutes break and then we'll get back. Rohit, can you show me the chat box? Okay, some very general defect, color centers. So color centers are also the point defects. Okay, uh, very common color center that you all must have heard about at least once is F center. F center is nothing but an anion vacancy occupied by an electron. Okay. In NaCl, how does it form is you have NaCl, you expose it to sodium vapor, heat it and expose it to sodium vapor. So what happens is sodium dissociates into Na plus an electron. Now this sodium ion combines with a chloride from your interior of the crystal structure. Chloride moves outward to the surface. It combines with Na and it exists as an extension to the NaCl crystal on surface of it. But meanwhile, this electron that is given out, for the sake of electroneutrality, it goes inside and occupies the chloride ion. Now, what happens is this, because it is surrounded by a particular three-dimensional arrangement. So this acts as a kind of a particle in a box thing. And all of you remember the particle in a box has got different energy level. And those energy level, they fall in the visible region. So because of that, this particular material, any material, when it adopts, when it gets F centers, it becomes colored because it absorbs in the visible region. And if you can relate to what I'm saying, that it is kind of a particle in the box, then you will always be able to appreciate that the size of this box is actually dependent on the material's crystal structure, right? That means the color that this solid will exhibit will not depend upon what vapor you heated it in. It actually will depend upon the crystal structure of this particular material. Now, what I want to say here is that if you had heated it in the rubidium vapor or potassium vapor, the color that your sodium chloride crystal will adopt will always be greenish yellow. Okay, so that means NaCl, if I had exposed it to sodium vapor, it would have been K giving K plus plus electron. This K plus would have combined with KCl, settled on the surface of NaCl. This electron would have moved inside, and it really would not have known that whether it has come from Na plus or K plus. And the color of the material will still be greenish yellow. Similarly, KCl, if you heat it in potassium vapor, sodium vapor, it will give you a lilac color. It's kind of violet color, basically. Okay. And how can you investigate? Of course, we'll talk about how can you investigate different types of defect. But here, since we are talking of an unpaired electron, color centers can be investigated by ESR because we're talking of unpaired electron. What is ESR? Is electron spin resonance. Now, these color center can be produced by exposing to the radiation also. I work with XRD very extensively, and many a times we observe that we record XRD of the material, and specifically if we have taken longer runs, expose it to XRD for like longer duration of time, then sometimes the material shows a tinge of color. In case of NaCl, this might happen here not because of sodium vapor and all, but due to the ionization of the chloride ion itself. What it happens is the chloride ion forms chlorine atom and it gives away an electron. And this electron then, this particular combination of this, it has got a transition in the visible range that gives the material its colors. So for example, one particular defect is H-centered. As I told you, it forms a chlorine atom, and this chlorine atom can combine with a nearby chloride ion to form a chlorine molecule ion. Chlorine molecule ion has got energy levels in the visible region. When this chlorine molecule ion occupy two sites in the crystal lattice, as is shown here, this is called a H center. Okay. And when this particular chlorine molecule ion occupies only one side, like this, here everything else is undisturbed and it is occupying one side, then this is called V center. Simply the nomenclatures. This is for mostly the physicists who deal with the defects and defect equilibria. It is for them. Some other type of color center which would be good for you to know if you come across in some literature papers and so on. M center, when you have a pair of nearest neighbor F center, okay? Two F centers are lying close together. They are called M centers. R center, if you have three neighboring F center and they lie on the 1, 1 plane of the unit cell, this way, that is called an R center. Okay, F prime center, you have two electrons on one anion vacancy. Energetically, a very high energy consuming scenario, but this is sometimes they might happen, when you pass radiation on the material. A material being exposed to irradiation is not an equilibrium thing. So there are many things that might happen which are energetically not actually feasible. So just one case is F prime center. It is two electron on one anion vacancy. Fa center is actually an F center. Here your F center was surrounded by all Na plus. If one of these Na plus was K plus, that is called an F center. That is, Fa center is when one of the cations surrounding the F center is a heteroion. It is not belonging to that particular material. All right. Okay. Now, this was thermodynamics defect and F centers. The classification of the defect based on dimension. Okay, one more thing. Whatever classification we talk about, we are not going to have different defects for a particular classification. Like, it's not that my classification A will have 1 to 10 defect and classification B will have 11 to 20 defects. No, same defects, but by virtue of how they are created, what is their dimension, they fall in all the classification. For example, here I would be talking about classification of defects based on dimension. Dimension means size. And zero dimensional defects, which are also called point defects, because they occupy ideally, I would say ideally, I will explain later why. Ideally, they occupy one lattice side. Okay, so they are called point defects, and they include vacancy interstitial, they include Schottky, they include Frenkel, and they also include color center. Schottky and Frenkel we also read were thermodynamic defect. That means changing the classification or talking about a different classification scheme is not going to change the defects for you. So coming back to this particular classification classifies the defect based on their size. So 0D, as I mentioned, are the defects that occupy one lattice side. 1D defects are those which occupy uh, at least a line, as the name suggests, one-dimensional defect or a line defect. They can also be called as one-dimensional arrangement of point defects. So we have two types of line defects, edge dislocation and screw dislocations. Then we have 2D defects. 2D defects means the span is at least over a two-dimensional area and their thickness is, let's say, few atomic diameters. So there you have grain boundary, you have twist boundary, we'll talk about them, tilt boundary, stacking fault, phase boundary and twin boundaries. Three-dimensional defect are actually what you can observe by your microscope. In fact, these two also you can observe by microscope. Those are pores in your materials. Those are cracks in your materials. The bubbles in the material, basically the defects that occupy a particular volume. All right. Okay. Let's talk about line defects today and then we'll close our session. So line defects are also called dislocations. They are one-dimensional or point defects arranged in line. They're also called line imperfection and mostly, okay, one very, very important difference between your point defects and point defects in specifically Schottky and Frenkel, not the color centered, versus 1D, 2D, 3D defects is that while your Schottky and Frenkel are thermodynamically generated defects, these defects are not thermodynamically generated. They are created by external perturbation. They do not lead to lowering of free energy. Okay. They only create instability in the material, but Howsoever, but still they are created, and they also have their importance because they very strongly affect the mechanical property of the material. Okay, many of them are formed during solidification when you're solidifying a crystal or when you deform a material. They affect the mechanical, electronic, and photonic properties of the material, and they also occur in very high densities of the order of 10 raised to the power 10 line defects per meter square of the area. They are not thermodynamically generated, and it is an important point to remember. Here, your enthalpy increases much more rapidly than the entropy. As a result, your delta H term makes it unfavorable as compared to minus D delta S term. Now, there are two basic types of dislocation. They can many dislocation, but they can always be defined in terms of combination of these two. So, what are those two? Edge dislocation and screw dislocation. Okay. So, edge dislocation is simply, just look at this particular figure. It is nothing. Now, this is a perfect cube. Okay. You can also assume it as the plane of atom parallel to each other along the C axis. Now, suppose there was this middle plane which started from the top, but it parted ways in the middle. It could not go till the end. And when that happens, then this is called edge dislocation. So where is that dislocation? Where is that defect? If I put my pen on this particular point where that plane has stopped, then that particular line going inside the screen, going inside this cube is the edge dislocation. This particular surface would also look like this. Okay. When your material was completely without any edge dislocation, this is how the atomic arrangement was. When there was a plane which started from the top but parted midway, this is what will happen around this particular area. Now your edge dislocation from this point is going inside the screen. The atoms which are above the edge dislocation, they're kind of constricted, but the atoms which are just below the edge dislocation, they have a lot of room to breathe. Now, this bond distance, which is smaller than the normal and which is bigger than the normal, according to the potential energy diagram, will have higher energy. That is the reason your edge dislocations are associated with higher enthalpy and they are not thermodynamically generated defect. One more representation is this, okay? This is your perfect cube. Nothing happens. Now you imagine you are actually trying to put your hand on this particular face. Let's say you divide it into some 4 cubes and then you try to apply the pressure in this direction. What will happen is your front face will join, let's say, the second face. Then your second face plane starting here will join the third here, third to fourth, fourth to fifth. Ultimately, the one that is on this boundary, the plane that is on this boundary, that is this plane, will not have any counterpart in the lower half of this cube. This particular line EF is called your edge dislocation. Okay. And then edge dislocations are represented by either this or this, depending on whether the plane starts from the top and part midways or it starts from bottom and part midways. I hope this is clear. Okay, how do we define? You have to quantify. When you say that my material has got the edge dislocation, you have to quantify it. That is given by something called a Burger's vector, and it is very easy. Not going into any technical detail. Suppose this was your completely ideal crystal structure. You started from the point P, you moved in this direction, then you moved, let's say, by 4 circles, moved here by 5 circles, moved here by 4 circles, moved here by 5 circles, you're back to P, right? Here, when you have edge dislocation, you started from point P, move by 4 circle, move by 5 circle, come back by 4 circle. If you again go by 5 circle, you will reach the point Q, which is not the starting point. To reach the starting point, you will have to come back by a distance B. Now, this direction of B and the magnitude of B gives you the quantification of Burgers vector. I hope it is clear. The magnitude of B is the magnitude of edge dislocation. The direction of B is the direction of edge dislocation. Okay. Also, what I want to say is, yeah. Now your Burgers vector, if you see, it is this. Okay. But your edge dislocation is going inside the screen of the material. That means in case of edge dislocation, Burgers vector is perpendicular to your edge dislocation. This is something that you have to remember. All right. Now, if you be with me, just observe at this particular cube. Okay. Now divide it in such a way that you cut this cube this way, and then you cut this cube this way. Okay. Now place your hand on this particular section and try to move it in this direction. Okay. And here what you did is you placed your hand here so that the crystal cube was not moving in this direction beyond this particular line. But here you are not stopping it. What will happen? It will go here, and your front face, which was regular, it has now become like this. Or in terms of atom, if I tell you, these are your planes perpendicular to this direction. This 1, 2, 3, and 4 were joined to each other when it was regular. 5, 6, 7, 8, and 8 was joined to 5. 9, 10, 11, 12, 12 was joined to 9, and they were joined together. But when the screw dislocation happened, that is, you move this plane in this direction. Now 1 is joined to 2, 2 is joined to 3, 3 is joined to 4, but 4 instead of being joined to 1 is actually joined to 5. 5 to 6, 6 to 7, 7 to 8, 8 instead of 5 is going to 9. So what actually were parallel earlier have now become a helix. It is like, in Bollywood movies, you see those stairs, you have a pillar, and around that round stairs they go about. It is something like that helix. Or it is also like your screwdriver when you move it inside or outside. Because of similarity to screwdriver, this particular dislocation is called screw dislocation. Okay. And as you can see, this also goes, and here also, if I want to define the Burgers vector, here I can make a perfect loop. But here to make that loop, I have to move this particular extra distance. So this is my Burgers vector. And unlike edge dislocation, here Burgers vector is in the direction of screw dislocation. In edge dislocation, it is perpendicular. Here it is parallel. Okay. So this is how we quantify screw dislocation by using the Burgers vector. So I would want to stop here because I know it is a little too hard on understanding it. But once you close the class, close your connection, just try to go through this figure again, because if you understand it now, you will not forget it. But if you don't look at it now or immediately after the class, it will be very difficult to remember this particular thing. Okay. So that is it from my side. The time is over. And if you have any doubt, I'll wait for 2 minutes, else we'll close the class. And now I shall meet you as we wrote in the chat box on Friday. All right, in that case, we end our lecture now and wish you all a very good day. And we'll meet now on Friday. Okay, thank you very much.